Okay, this problem is from the section on related rates, 3.11. And it says hot air balloon is rising vertically. Rising vertically is tracked by an observer located 4 kilometers from the liftoff point. At a certain moment, the angle between the observer's line of sight and the horizontal is pi over 5, and it is changing at a rate of 0.2 radians per minute. How fast is the balloon rising at this moment? Okay, so for these problems, I always like to start with a picture. So we have a hot air balloon. Okay, pretend that's a hot air balloon, and it's rising vertically. It's going up. And maybe this is where it came from. Here's the ground. And here's this person who's looking at it. I guess their feet should be on the ground. Just imagine this person is on the ground. And we know that this distance between this person and the launch site is 4 kilometers. That is not changing. Okay. And they said the angle between the observer's line of sight and the horizontal, at a certain moment it's pi over 5, but that angle, it's changing, right? As time goes on, the balloon goes up and this angle will change. So I'm going to call that theta. And they ask how fast is the balloon rising at this moment? That means how quickly is this vertical height changing, right? So how high up is the balloon at a given moment, and how quickly is it rising up? Okay, so I guess what we know is when theta equals pi over 5, what do we know? When theta is equal to pi over 5, then it says the angle is changing at a rate of 0.2 radians per minute. So the rate of change of theta is d theta dt. Maybe I should write this underneath. .2 radians per minute. Okay. And what do we want? We want to know dh dt at this time. Okay. So now that we've set up our variables and we've translated the words in the problem into what that means for our variables, we can try to solve this problem. So we want to relate the variables that we have, theta and h. Those are the two things that are changing over time. The balloon's rising up, so h is increasing, and this angle is changing. Okay, and so let's look at this. Well, we have this right triangle. It is a right triangle. And we know that tangent of theta is opposite over adjacent, which is h over 4. Okay. And I might say, why don't we, in fact, be a little bit more explicit and show that we know that theta and h are things that depend on t. They're varying over time. So when we take the derivative, this will remind us that we have to use the chain rule here. So if we want to, we've related the variables, but now if we want to relate their rates of change, we have to take the derivative of both sides. So let's differentiate. The derivative of tangent is secant squared. And remember, because we're differentiating with respect to t, we have to differentiate this theta of t inside, and we'll get d theta dt, and that's equal to, well, we can pull out the 1/4, that's a constant, and just have dh dt. Okay, great. Now, what do we know? We know at the time that we care about, d theta dt is 0.2 radians per minute, and we know that theta is pi over 5. So let's see, at the time we care about, we can plug in and say secant squared of pi over 5 times 0.2 equals 1/4 dh dt. So dh dt, that's the thing that we wanted to solve for, that's equal to 0.8, let me make that neater, 0.8 times secant squared of pi over 5. And if I had a calculator, I could tell you what secant squared of pi over 5 is, but for now I'll just leave it like that.